Assalamualaikum and hi. My name is Dr. Nur'Ain Idris from Universiti Hussein on Malaysia, UTHM, and today I would like to present part of my research, which is the paper entitled "An Improvement in Boundary Treatment of Solid Boundary Using ISPH Approach." Okay, as a motivation, we know that boundary treatment of the particle method is one of the important issue for ensure the accurate solution or accurate simulation occur, and we also it is also necessary in order to avoid the penetration into the wall or solid boundary, and this research become actively and still being searched, being one of the active research area, and and therefore we come up with the aim of this study is to propose the proper boundary treatment of solid boundary, which is the Newman fully conditioned is adapted, right? So as a introduction, we know that simulation require a proper technique or proper method, okay, especially for the deformation and large deformation, so that a mesh-free method is take into account, is introduced, and this method is able to treat especially for the large deformation, whereby the system is treated as a set of particles and the variables such as mass, momentum, energy, and position are computed at each particle. Which is have the features of the Lagrange, and the measurement methods are used for solid mechanics as well as for the fluid dynamic. And one of the approach by using mesh-free particle method is using the smooth particle hydrodynamic, which is SPH, and this is the fundamental of the SPH. Okay, whereby the fundamental SPH is based on the interpolation method. Okay, at first the target body is discretized into a particle like this, as shown here, and then the target particle physical quantities are being interpolated based on the concept of the weight average of the neighboring particles, as called as a smoothing kernel function. Okay, smoothing kernel function, and the SPH integral equation can be approximated by the summation contribution of the neighbor particles in the support domain. Okay, and this SPH approximation equation is applied for the governing equations such as the Navier-Stokes equation and mass conservation law. In this study, the stabilized ISPH is used, and the features of this technique appear in terms of pressure Poisson equation. Okay, and the original ISPH method, the PPE, is derived from assumption of density invariance. Okay, from the on the other hand, our formulation allow the compressibility in the mass conservation law, and we get the different sources in terms of the PPE, pressure Poisson equation. Then we put a small alpha here to decrease the second term effect, and the alpha is assumed to be 0.01 empirically. The conventional or the pseudo Newman condition is put the virtual marker in the water domain. Okay, and in order to prevent the penetration of the water particle into the rigid body, the normal component of the water particle velocity have to be 0, and this condition called as a non-uniform pressure Newman condition. And the virtual marker is located and put symmetry to the wall particle. Okay, with the distance. Okay, then the physical quantity on the marker was interpolated by using the ISPH approximation, right? Same condition, but that one is for the pressure, and the same condition also for the velocity, which is the virtual marker is put symmetric to the wall particle, and there are two conditions, can be three condition, which is the slip condition, non-slip condition, or optimize the condition between the slip and non-slip condition. Okay, then for the pressure condition, we already discussed in the previous one, whereby the virtual marker is put the symmetric to the wall particle, and the normal component of the velocity gradient should be 0 in order to prevent the penetration of water into a rigid body. Then, in this study, the proposal of the implicit Newman boundary processing method, which is the boundary condition of the pressure fluid, is to be satisfied by the original. We can see here the pressure surface should represent the dielectric condition, which is P equal to 0 due to the atmospheric pressure, and on the wall it should represent the pressure Newman condition. The conventional particle method use you can see the model of the entire circumference. The red one shows the dielectric condition, which is the Newman condition was affected. Okay, then we come up with the solution. Try to change the position of the virtual marker. So the position of the virtual marker is located at the surface, at the boundary, wall boundary. Okay, so the fixed coefficient matrix to satisfy the Newman condition through the marker were placed on the wall. Then the equation should solve by using this metric. Then we come up with the some testing in order to validate or check the simulation of the proposed boundary treatment. We did a verification of the hydrostatic case by using include the features of the incompatible surface, then the validation with the dam break flow, and lastly we did the demonstration of the Bunny-Stanford. Okay, so this is a verification with the hydrostatic test. We can see with the tank height 0.2 meter, length 0.2, 0.2, we make a measuring point at the center of the tank, and the same dimension 0.2, 0.2, 0.2 dimension, but the bottom of the tank was changed into a incompatible surface in order to check the pressure on the boundary especially near to the wall area. So we found that on the right side is the represent the conventional method, which is the pseudo Newman boundary condition, whereby the left side shows the where the Newman boundary treatment is fully in the fully condition. Okay, so this is the results of the hydrostatic compared with the theoretical value, and it shows that when the Newman fully condition is give a satisfied results, especially near to the boundary, near to the wall boundary. Then we make a validation with the dam break problem, and this is experiment was carried out by Lobosky in 2014, and we did the same geometric as the experimental, and also with the opening gate, the velocity of the opening gate. And in this in this paper, we focus on the two sensor located in the uh, two sensor from the experimental, which is sensor 2 and sensor 4, uh, with the distance from the bed is the 30 millimeters and 80 millimeters from the bed of the tank. Okay, and this is the results. Okay, I will show it at the beginning. Okay, the results of the simulation compared with the experimental. Okay, and we make a comparison of at a certain time snapshot, and it shows that a good tendency of the movement of the water tank, and and also the pressure. We can see the contour, the pressure contour is reasonable, acceptable, which is the, we can show it can you can see the pressure gradient from the static condition before an opening gate until the gate is removed, and the impact after it's hit the wall, which is shows the higher pressure. Okay, and this is um, the data that we get from the measured from the simulation compared with the experimental for the two sensor. We can see here the red one is from the simulation by using the proposed boundary treatment. Okay, and last but not least, the Stanford Bunny demonstration. We can see here the the pressure of the bunny, and also the water shows the acceptable acceptable results, which is there is no penetration occur along the simulation. All right, at the end, thank you.